Welcome to the lecture series on differential equations for undergraduate students. Today's topic is higher order non-homogeneous linear differential equations. Till now we have done homogeneous linear differential equations with constant coefficients and with non-constant coefficients, and we had learned about their solutions. Today we will learn about non-homogeneous equations of nth order. The standard form of these equations is as yn plus pn minus 1x yn minus 1 plus so on p1x y dash plus p naught x y is equal to rx. Here this pn minus 1x, p1x, p naught x, they are all function of x. We are not now differentiating with the constants and non-constant, we will just treat it as simultaneously. Yn as usual is the nth derivative of the unknown function y, yn minus 1 is the n minus 1th derivative of the unknown function y, and so on, and rx is also a function of x. Now here, because it is non-homogeneous one, we are assuming that this rx is not 0. So we have learned that is its corresponding homogeneous equation would be simply yn plus pn minus 1x yn minus 1 plus so on p1x y dash plus p naught x y is equal to 0. That is, the right hand side will make the 0. This is the corresponding homogeneous equation of this. Now as we have done in the second order non-homogeneous equations, here also the general solution of this non-homogeneous equation is of the form yh plus yp. What is this yh? yh is the general solution of this corresponding homogeneous equation, and yp, this is a particular solution of this non-homogeneous equation. Now this homogeneous equation which we are seeing here, we had learned whether this coefficients were constant or they were function of x. We had learned that method how to solve this homogeneous equation, that is this part yh we can calculate for the homogeneous equation. So here what is left to learn is to find out yp, that is a particular solution for this non-homogeneous one. So first we will see the existence and uniqueness of the solution. If I do have a non-homogeneous linear differential equation of the form yn plus pn minus x yn minus 1 and so on plus p1x y dash plus p naught x y is equal to rx, where the coefficients pkx, that is this pn minus 1x and so on, they and this right hand side rx, they are continuous on some interval I, then the general solution exists and include all solutions. That says is the solution of this equation would be exist if I do have these coefficients as continuous on some interval as well as the right hand side is also continuous on that interval, then the solution will exist on that interval. Here you see in the standard form we are taking the coefficient of yn as, that is the nth derivative, as 1. Moreover, it says is the general solution includes all solutions, that is all the solutions of this differential equation can be obtained from the general solution. We do not have any singular solutions here. What is the initial value problem of this one? Initial value problem consists this non-homogeneous linear differential equation with n initial conditions. What are those initial conditions? Those initial conditions are y at x naught is equal to k naught, y dash at x naught is equal to k1 and so on yn minus 1 x naught is equal to kn minus 1 for some x naught in that interval I, where we are talking about the function is continuous. So we are saying is we are giving some initial values of the function and its n minus 1 derivatives, that is first derivative, second derivative till n minus 1th derivative at some point x naught we are giving the value. If this initial conditions are being given, then we can find out from the general solution the values of the constants and that solution would be unique, that is initial value problem has a unique solution. So what we had learned? We had learned if the coefficients on the right hand side is continuous on some interval, then the general solution will exist for this equation, and the general solution as we had just learned in the previous slide, that it would be of the form yh plus yp, and if initial conditions, any initial conditions are being known, then there would be a unique solution for this one. So, now we would learn how to find out this yp. So, methods to find yp, as in the done we have done this part for finding out this particular solution of this non-homogeneous equation, as we have done in the case of second order equation. Here also we will learn two methods. The first method, method of undetermined coefficients, and second, the method of variation of parameters. Do you remember that we have already done these methods in the case of second order linear differential equations, non-homogeneous one. Here we are having nth order equation. Again we will learn these methods. So, first learn this method of undetermined coefficient. This method is applicable in certain special cases. What are those special cases? First is that nth order linear differential equation has constant coefficients, and that is those p n minus 1 x, p n minus 2 x and p 1 x, p naught x, they should be the constant, they should not contain any function of x, and R x is of the special form. What is that special form? Either it is e to the power a x or a polynomial such as x to the power n plus b 1 times x to the power n minus 1 and so on plus b naught times x, or it is of the form of cos b x sin b x. That is, either it is of form sin b x cos b x e to the power a x or of a form of polynomial, and the coefficients p naught p 1 x, all these are constants. Only then this method is applicable. This is as usual as we had learned. What is this method says? This method says is that if R x contains the term of e to the power x kind of thing, that is here we are saying is k times e to the power gamma x, then we choose the yp as c times e to the power gamma x. You see that is same constant we are having as we are having is in exponential function, but here this constant is changing c. This constant is called undetermined coefficient, and we are determining this coefficient by putting this function as a solution of non-homogeneous equation. So, the function and its derivative will keep in the given equation, and from there we will determine this coefficient c. Similarly, if my left hand side, that is if my R x is of the polynomial form. So, here I have written only k times x to the power n. It is not necessary, it may be simple polynomial, that is k n times x to the power n plus k n minus 1 times x to the power n minus 1 and so on. But whether it is having here the complete polynomial or not, it does not matter. The choice of yp must be the polynomial of degree n, that is k n. Here you see this is capital K n x to the power n plus k n minus 1 x to the power n minus 1 and so on plus k 1 x plus k naught, that is I do have n plus 1 undetermined coefficients. This we will determine by putting this function and its n derivatives in the given equation, and then find out from the equating it from the right hand side, we would find out what are these coefficients. Similarly, if my R x is of this form cos omega x or sin omega x, whatever it may be, whether it is having both the things or it is simple one, we just choose this function. Similarly, if I do have is that special form is e to the power alpha x into cos omega x or e to the power alpha x and cos sin omega x, we would again have here this yp as e to the power alpha x times a sin omega x plus b cos omega x. Here again this undetermined coefficients are a and b. So, what is the method of this rule of this method? Basic rule. Just now I have defined the basic rule, which says is if this equation, for this equation y n plus p n minus 1 x plus into y to the power y n minus 1 and so on plus p 1 x y dash plus p naught x y is equal to R x, where my p n minus 1 x, p 1 x and all these p naught x, they are constants, not the function of x, and R x is of any form which has been given in this previous table, that is just now I had explained you the first column of the table. Then choose the corresponding function y p in the second column. That is what is my basic rule, and find the value of undetermined coefficient by putting y p and its derivative in this given equation. Now, it may happen That is, when we are choosing this yp, I may be having that choice of yp is already in the solution of the homogeneous equation of, that is the corresponding homogeneous equation of this equation. That says is then that yp will not be linearly independent of those homogeneous equation solution, while we require yp to be linearly independent of that one. That says we require certain modifications. So, the second rule is called modification rule. What is this modification rule? If any term in the choice of yp is also in the solution yh of corresponding homogeneous equation of this non-homogeneous equation, then multiply the choice yp by x to the power k, where k is the smallest positive integer such that no terms of x to the power k ypx is a solution of this homogeneous equation. Why we are saying here, if you do remember the second order one, there you said is that is multiply it by x or x square depending upon whether it is a single root or the single solution or the double solution of the corresponding to the single root or the double root of the homogeneous or the characteristic equation of the homogeneous one. Now, here since I am having is here a nth order equation, and we had learned in the homogeneous one that we will have actually multiple roots. That is, roots are not only single and double, we could have a multiple root of multiplicity k. So, if suppose I do have a root of multiplicity k minus 1, then we must multiply with x to the power k times ypx. That will make it sure, that is, if the root has multiplicity k, we would have that is x times and so on, we by the method of variation of parameter, that is all those would be in the solution. So, this will not be in the solution of this corresponding homogeneous equation. This is the modification rule. Again, we may have that the right hand side is consisting of those special functions, but they are a sum of those things. So, the third rule is the sum rule. Again, this is similar to that what we have done in the second order. If Rx is the sum of different functions given in the column 1 of the table, then choose yp the sum of corresponding function in the second column. Now, we had learned that is the rules are similar to that what are in the second order differential equations. Now, let us try one example to understand that how to apply this method. So, let us do one example. Solve the initial value problem. y3 plus 3y double dash plus 3y dash plus y is equal to 30 times e to the power minus x. Given initial conditions are y at 0 is 3, y dash at 0 is minus 3 and y double dash at 0 is minus 47. We see here we are having a third order differential equation. The coefficients again we are having is that the function y and its derivatives, they are occurring separately. So, it is a linear differential equation. Then we are having the coefficients of y, y dash and all those things, they are just constants 1 and 3. So, this is a linear differential equation with the constant coefficient. Right hand side is of a special form 30 e to the power minus x. This is not 0, but this contains a function which is of a special form of the exponential form. That says is we can apply the method of undetermined coefficient. So, let us just try the solution. First, we will find out the homogeneous equation. So, the corresponding homogeneous equation would be what? y3 plus 3y double dash plus 3y dash plus y is equal to 0. That is, we just make it right hand side as 0, that is the corresponding homogeneous equation. So, first we will find out the yh. For finding out the solution of this homogeneous equation, we require the characteristic equation of this one. Characteristic equation for this equation as we know would be lambda cube plus 3 lambda square plus 3 lambda plus 1 is equal to 0. If we see what is this lambda cube plus 3 lambda square plus 3 lambda plus 1, this is nothing but lambda plus 1 whole cube. So, what will be the roots? Roots are lambda is equal to minus 1 and minus 1, that is we are having a multiple root, rather a triple root. This is a third order equation and we are getting a triple root. So, what will be the basis of the solution for this homogeneous equations? As we do know earlier, the linearly independent solutions would be corresponding to this e to the power minus x. Then the second solution we will have x times e to the power minus x. Then the third solution we will have x square times e to the power minus x. These are three linearly independent solutions. So, YH would be C1 e to the power minus x plus C2 x times e to the power minus x plus C3 x square e to the power minus x. Now, we see right hand side is of this special form 30 e to the power minus x. If you remember, in our table we had is, that is, if it is a times e to the power gamma x, we should choose e to the power gamma x. That means, in the yp we have to choose e to the power minus x, but we are finding out e to the power minus x is a solution corresponding to a triple root. So, let us see it.
Okay.
This method of undetermined coefficient says, now we are having in the right hand side 30 times e to the power minus x. That means, I have to choose c times or a times e to the power minus x, but already we have seen that e to the power minus x is a solution corresponding to this thing. So, we have to use the modification rule. Modification rule says is that I have to multiply the choice of yp by x to the power k, such that x to the power k ypx is not a solution, is no term in this is a solution of this homogeneous equation. We have seen that in our one we have got e to the power minus x, x times e to the power minus x and x square times e to the power minus x, all are the solution of YH. So, we will choose here x cube e to the power minus x. So, you see I am having in my YH e to the power minus x, x times e to the power minus x and x square times e to the power minus x. So, what will be my choice of yp? This yp I will choose a times x cube e to the power minus x according to the method of undetermined coefficient with respect to the modification rule. Now, how to find out this a? We will put this yp and its derivative in the given equation. So, what will be its derivative? Yp dash would be a times 3x square minus x cube e to the power minus x. Yp double dash would be a times, now here 6x minus 3x square, that is into e to minus a to the power minus into e to the power minus x. Then the this derivative of e to the power minus x is minus e to the power minus x, and this coefficient is as such. So, that is what here what we are getting is that it is equal to a times 6x minus 6x square plus x cube e to the power minus x. What will be the third derivative? Again, first we will make the derivative of this function and write this function as such, and then derivative of this function and this function as such. So, we are getting a 6 minus 12x plus 3x square minus 6x minus 6x square plus x cube into e to the power minus x, which is equal to 6 minus 18x plus 9x square minus x cube times e to the power minus x. Now, the given non-homogeneous equation if it was y3 plus 3y double dash plus 3y dash plus y is equal to 30 times e to the power minus x. Now, substitute this yp 3 yp double dash and yp dash and yp in this one. So, what we will get? Substitution a times 6 minus 18x plus 9x square minus x cube e to the power minus x plus 3 times y double dash, that is 3 times a 6x minus 6x square plus x cube e to the power minus x plus 3 times y, that is 3 times a 3x square minus x cube e to the power minus x plus y, that is a times x cube e to the power minus x. This is equal to, this must be equal to 30 e to the power minus x. So, what we are saying is, this we are saying is that is a particular solution of this homogeneous, this non-homogeneous equation. That says is the function and its derivatives must satisfy this equation. So, now we want that this must satisfy this equation. So, if we simplify this left hand side and say that it must be equal to this one, we are getting is 6 a times e to the power minus x must be equal to 30 times e to the power minus x. What this implies? That my 6 a must be equal to 30 or a must be equal to 5. So, what I got the particular solution? Particular solution I got as 5 x cube times e to the power minus x. So, what will be my general solution of this non-homogeneous equation? That is y h plus y p. Y h is this one and y p is this one. So, what I would get? C 1 e to the power minus x plus C 2 x times e to the power minus x plus 3 C 3 x square e to the power minus x plus 5 x cube e to the power minus x. Now, you see this is the general solution. We are getting the terms e to the power minus x, x times e to the power minus x, x square times e to the power minus x and x cube times e to the power minus x. They are all linearly independent. So, this is the general solution. Now, we want the solution, we have to solve the initial value problem. That says is we have to find out in this general solution what are these general constants C 1, C 2, C 3, what are the values given those initial conditions. So, that must have a unique solution. So, solution of initial value problem. The given initial conditions are that y at 0 is 3, y dash at 0 is minus 3 and y double dash at 0 is minus 47. And our general solution is, again I have written it, C 1 plus C 2 x plus C 3 x square plus 5 x cube times e to the power minus x. Now, find out it's because we have to put the initial conditions for the first derivative and the second derivative. What are the first derivative and second derivative? They are minus C 1 plus C 2 x plus C 3 x square plus 5 x cube times e to the power minus x. That is differentiating this function first and keeping this as constant, then differentiating this function and keeping this as such. We are getting C 2 plus 3 C 2 C 3 x plus 15 x square times e to the power minus x, and y double dash again with the similar method we would be getting is minus C 2 minus C 1 plus 2 C 3 minus C 2 x times x plus 15 minus C 3 x square minus 5 x cube times e to the power minus x plus 2 C 3 minus C 2 plus 2 times 15 minus C 3 times x minus 15 x square into e to the power minus x. Now, put the initial conditions y at 0, that is when I put x is equal to 0. If here I am putting x is equal to 0, all these terms would become 0, this term would become 1. So, I would be getting is y 0 as C 1 which is given as 3. So, I am getting C 1 is equal to 3. Now, y dash at 0 is minus 3 is given. What will be y dash at minus at 0? If I put 0 in place of x in all these things, I would get from here minus C 1 and from here plus C 2. So, I would be getting minus C 1 plus C 2 which is equal to minus 3 as given. Now, since C 1 is we had already find out as 3. So, if I substitute this 3 over here, I would get C 2 is equal to 0. Now, the third condition is about the second derivative. In the second derivative, if I try to put x is equal to 0, I would get from this here minus C 2 minus C 1 and from here plus 2 C 3 minus C 2. So, I am getting is 2 C 3 minus 2 C 2 plus C 1 which is minus 47. We had already find out C 1 is equal to 3, C 2 is equal to 0. So, this gives me 2 C 3 is equal to 50. You could get it or C 3 is equal to minus 25. So, now we have got the 3 constants C 1 as 3, C 2 as 0 and C 3 as minus 25. So, what will be the solution of my initial value problem? I will substitute these constants in this general solution. I will get 3 minus 25 x square plus 5 x cube times e to the power minus x. This is the general solution, this is the unique solution of this initial value problem. You are getting is that single values, you are not getting the general constant C 1, C 2, C 3 here. Let us see how it looks like. So, I will take some other values for C 1, C 2, C 3. So, what will be the other solutions? Since the general solution is this one, if I choose C 1 as 2 and C 2 as 4 and C 3 as 6, I will get a solution as 2 plus 4 x plus 6 x square plus 5 x cube times e to the power minus x, and the particular solution we are already having is 5 x cube e to the power minus x of this of that homogeneous equation, non-homogeneous equation, and the solution of IP initial value problem, that unique solution we had already got this one. Let us take some other values for C 1, C 2 and C 3. Then that is 2, 4 and minus 16. So, other solution I am denoting it here by y. This would be 2 plus 4x minus 16x square plus 5x cube is equal to e to the power minus x. Let us see in the graph how they are looking like. You see here we are having this is yx, that is when I have taken 2, 4 and 6. This is yp, that is the particular solution. Particular solution when I have taken C1 as 2, you see is that is my graph would start from at 0 the function is 2. Similarly, in the other condition, other solution which I have taken is there also I have taken C1 as 0 and C2 as 4 and C3 as minus 16. So, this graph y you are seeing is again it is starting from 0, this 2. Initial condition set that C1 is 3. So, you see is this yi, that is the solution of initial value problem. This is starting from 3 and yp was the particular solution. Particular solution means is that is the general solution part is 0, that means my C1 must be 0. So, you are seeing is that it is starting from 0. You are seeing is that by different conditions we are getting different solutions, and this is the solution of your this yellow line. This line is the solution of initial value problem, and the solution space would contain all these kind of solutions. So, this is what this example says. Now, let us learn the other method of variation of parameters. Again we will go in the similar lines as we have already done in the second order one. First, this method is applicable to all those cases where the method of undetermined coefficient is not applicable. That is, I may have general non-homogeneous linear differential equation yn plus Pn minus 1x yn minus 1 and so on plus P1x y dash plus P naught x y is equal to Rx, where this Pn minus 1x, P1x, P naught x they need not to be constants and Rx need not to be of any special form, still this method is applicable. What is this method? This method says is, if I assume that y1, y2, yn are the linearly independent solutions of the corresponding homogeneous equation of this given non-homogeneous equation, then we by method of variation of parameters says we can find out the particular solution as u1x plus y1x plus u2x, y2x and so on plus unx, ynx. Do you remember that in the second order one we have taken u1x, y1x plus u2x, y2x. Now, here since we are having this n solutions of this corresponding homogeneous equation. So, we would have here n unknown functions u1, u2, un. This by method of variation of parameter we have to determine, that is how to find out this functions u1x, u2x and unx. They can be obtained as the solution of the system u1 dash x plus y1x plus u2 dash x times y2x and so on plus u1 dash x y1 x is equal to 0, u1 dash x y1 dash x plus u2 dash x y2 dash x and so on, u2 un dash x plus yn dash x is equal to 0 and so on, will have the nth equation as u1 dash x times y1, that is n minus 1th derivative of y1 plus u2 dash times n minus 1th derivative of y2 and so on, un dash times the n minus 1th derivative of y1, yn is equal to 0. How we are getting this one? This what we are doing is, that is the choice of this yp which we have taken as u1x, y1x plus so on unx, ynx, that and its derivatives we are putting in the non-homogeneous equation, and from there we are trying to satisfy, that is it should satisfy the solution. So, we are getting, since each y1, y2, yn is the solution of corresponding homogeneous equation. So, from there we are getting this system of equations. Now, if we see the system of equations, what the matrix we would be getting, the determinant of this system is nothing but the Wronskian of y1, y2, yn. So, what will be basically the solution of this one? The solution would be that ui dash x would be wix upon wx into rx for all I 1 to n. What is this wix and wx? Wx is nothing but the Wronskian of the solutions y1, y2, yn. Since y1, y2, yn are the basis of the corresponding homogeneous equations, so this will never be 0, that is we can always divide it by. And what is wix? This is the determinant obtained from wx by replacing the ith column to 0, 0, 0, 1. This is I am just giving you the method how to find out the solution with the system of equations. Then what will be my ypx? Ypx would be simply y1x integral of w1x upon wx rx dx plus y2x integral of w2x upon wx rx dx and so on, ynx times integral of wnx upon wx rx dx. That is ui dash x are this one. So, ui x would be simply the integral of this with respect to x, and that would be. So, by this method of variation of parameter, this is the method how to find out the particular solution of the given differential equation. Now, let us do some examples to find out this. In other words, yp also we could write as summation I is running from 1 to n yix times integral wix upon wx rx dx. This is just the notational form to write this lengthy expression as in the simpler form. Example, find the general solution of y triple dash plus y dash is equal to tan x in the interval minus pi by 2 to plus pi by 2. We see here this is linear differential equation, the coefficients are constant, but the right hand side is of not of the those special forms. So, we have to use the method of variation of parameter. Let us see how we go for the solution. First, we will find out the general solution of corresponding homogeneous equation. So, the given differential equation is y triple dash plus y dash is equal to tan x. So, associated homogeneous equation would be y triple dash plus y dash is equal to 0. Its characteristic equation would be lambda cube plus lambda is equal to 0. Factorization, lambda times lambda square plus 1 is equal to 0. The roots would be that lambda is equal to 0, lambda square is equal to minus 1, that is the complex conjugate. So, the roots would be 0 and plus minus I. So, we are having one real root and a pair of complex conjugate roots. So, what will be the three linearly independent solutions, that fundamental system of the solution for this homogeneous equation, that would be 1 cos x and sin x. So, what will be yh? Yh would be c1 plus c2 cosine x plus c3 sin x. Now, for finding out the yp, we would use the method of variation of parameter. For that, we require the Wronskian of these three solutions and the different Wronskians. So, for particular solution yp, this method of variation of parameters, the Wronskian of the three solutions 1 cosine x and sin x, its derivatives 0 minus sin x cosine x, derivative of 0 is 0, derivative of minus sin x is minus cosine x, derivative of cosine x is minus sin x. This determinant if I solve, I would get sin square x plus cos square x, which is equal to 1. Then the different determinants, that is wi. So, first w1 says is that I have to change this first column by 0 0 1. So, the first column is being changed by 0 0 1, rest of the columns are as such. If we see what will be this determinant would be cos square x plus sin square x, that is it is again 1. What will be w2? W2 means the second column I have to change to 0 0 1. So, the second column has been changed to 0 0 1 and the first column and the third column is as such. Now, if I just open with respect to the first column, I would get it as cosine minus cosine x. W3, the first two columns are as such, the third column 0 0 1. Again, I am opening with respect to, expanding it with respect to the first column, I would get it as minus sin x. So, what we have got? We have got Wronskian as 1, w1x as 1, w2x as minus cosine x and w3x as minus sin x. So, what should be our ui's? And rx is tan x. So, my u1x would be W1x upon Wx Rx dx. W1 was 1, Wx was also 1, Rx was tan x. So, what I would get? Tan x dx. Its derivative is, its integral is log sec x. Then u2x, W2x upon Wx Rx dx. W2x we have got minus cosine x. Wx is 1, Rx is tan x. So, I would get minus cosine x into tan x dx. Minus cosine x tan x gives me minus sin x. Minus sin x dx, its integral is cosine x dx. So, we have got u2 as cosine x, u1 as log sec x, u2 as cosine x. u3, similarly it should be W3x upon Wx into Rx. W3 minus sin x, W1 Rx is tan x. So, we are getting minus sin x tan x dx. This will integrate by parts. So, we would get is cosine x tan x minus cosine x sec square x dx. Cosine x tan x is nothing but the sin x. Integral of this is integral of sec x dx. Integral of sec x is log sec x plus tan x. So, what we are getting is u1 as log sec x, u2 as cosine x and u3 as sin x minus logarithmic of sec x tan x. So, yp u1x y1x plus u2x y2x plus u3x y3x. Since we are having this third order one, so we will have only 3 ones. u1 and u2 and u3 just now we had obtained as such. y1 if you remember was 1, y2 was cosine x and y3 was sin x. So, write it u1 y1 log sec x, u2 y2 cosine square x, u3 y3 sin square x minus sin x times log sec x plus tan x. Now, this cos square x sin square x, this will become as 1. So, finally, yp I am getting is log sec x plus 1 minus sin x log sec x plus tan x. This is what is the particular solution of the given non-homogeneous equation. The general solution we had already find it out in the terms of C1 plus C2x cosine x plus C3 sin x. So, the general solution of the non-homogeneous equation yh plus yp would be C1 star plus C2 cosine x plus C3 sin x plus log sec x minus sin x log sec x plus tan x. You see here C1 star I have chosen as C1 plus 1 because 1 we are getting from here in the particular solution and C1 was from here. So, that is what we had put it in the constant terms, that is all. So, this is what is the solution of general solution of the given homogeneous given non-homogeneous equation y triple dash plus y dash is equal to tan x. Again put certain values and see how they are looking in the graph. This is what is our general solution. If I choose C1 star as 3, C1 star is C1 plus 1. So, I am choosing that is whatever it may be the value. So, C3, C2 is 5 and C3 also as a 5. So, I am denoting this solution by yx. So, this should be 3 plus 5 cosine x plus 5 sin x and plus this terms log sec x minus sin x times log sec x plus tan x. Let us choose another values for this one, that is 4, 5 and 6. So, what will be the this I am denoting by y1. So, 4 plus 5 cos x plus 6 sin x and then the particular solution, this part is as such. Another set of values 10, 5 and 7. So, what this y2 I am denoting, this is 10 plus 5 cos x plus 7 sin x and the particular solution part as such. Let us see how this graphs of these 3 solutions looks like. That is, I have chosen this yy, yy1, y2 and this yp. Yp means is that log sec x plus 1 something. So, you see here we are having is this yp. Yp is this solution which you are having is that is this yellow line, this is yp, that is log sec x, and this then we are having is that yy is the solution which we have chosen as at 0, that is we have taken the value as 3. So, C1 star 3, C1 star is that C1 plus 1, that is my C1 would be 2, that is what we are having it here is that it should be somewhere going like up, and like that we are having this different solutions y1 and y2. So, these are the graph it is looking like, that is between minus pi by 2 to plus pi by 2. We are not having any values more than that, because the solution is existing only over there. Let us see one more example, because in this example we had the homogeneous part as constant coefficients. So, solve the non-homogeneous Euler-Cauchy equation x cube y triple dash plus x square y double dash minus 2 x y dash plus 2 y is equal to x to the power minus 2. Now, we are having is that this is not in the standard form first thing. So, when we would apply the method of variation of parameter, we will have to check it that we have to change it to the standard form. Let us first start from here. We are having that coefficients are also not the constants, and the right hand side this is not of the form of polynomial, this is x to the power minus 2. So, again we have to use the method of variation of parameter. See how we solve it. The associated homogeneous equation corresponding to this non-homogeneous equation would be x cube y triple dash plus x square y double dash minus 2 x y dash plus 2 y is equal to 0. To solve this, we require this is nothing but the third order Euler-Cauchy equation. We do know that in the Euler-Cauchy equations the solution is of the form y is equal to x to the power m, and when we are putting this y as x to the power m and its derivative in the solution, we are getting some auxiliary equation in the terms of m. What is that auxiliary equation? That is, I have to put here y triple dash. So, what will be the third derivative of x to the power m? Of course, m into m minus 1 into m minus 2 times x to the power m minus 3 and so on. So, what the auxiliary equation we are getting is m into m minus 1 into m minus 2 plus m into m minus 1 minus 2 m plus 2 is equal to 0. Let us simplify this equation. It gives me m cube minus 2 m square minus m plus 2 is equal to 0. So, what we have got, this is the auxiliary equation. We have to find out the roots of this equation, so that we can determine what will be the solution of this Euler-Cauchy equation. So, factorization gives me, we have to factorize this, we see it from here, that is 1 would be one root. So, we just make it as m cube minus m square plus m minus 2 m plus 2 is equal to 0. Taking in from the first two terms the m square common, from the second two terms minus m common, from the last two terms minus 2, we would be getting is m minus 1 into m square minus m minus 2 is equal to 0. Again factorizing this second term, we get is this is m minus 1 into m plus 1 into m minus 2 is equal to 0. So, the three roots of this auxiliary equations would be minus 1 corresponding to this 1 and 2. What will be now? Three solutions, the basis of the solution. We do know that it should be x to the power m. So, what we would get here y1 as x to the power minus 1, which is as 1 by x, y2 as x and y3 as x square. We do know that these three solutions are linearly independent. We want to find out the particular solution for the non-homogeneous one. For that we require the Wronskians and the different determinants. So, Wronskians of these three solutions, 1 by x, x square, its derivative is minus 1 by x square, 1 and x square is 2x. Again its derivative, that is second derivative of this one or the derivative of this one, 2 by x cube, its derivative is 0, this derivative is 2. If I evaluate this determinant, so I am just doing little bit determinants. So, we are making these two entries in the first column as 0 by multiplying the first row by 1 by x and adding to the second row, then multiplying the first row by minus 2 by x square and then adding it to the third row, we do get this determinant. This determinant we do know by the method of determinants that this will not alter the value of the determinant. What we do get from here, if I expand this determinant with respect to first column, I would get 1 by x times 6 by 6. So, I am getting is it is 6 by x which is of course not 0. So, they are the 3 linearly independent solution, we were already knowing it, they are not 0, and this is what is my W. Now, let us calculate my W1, W2 and W3, so that we can find out that U1, U2, U3. YH of course C1 times 1 by x plus C2x plus C3x square. For particular solution W1, the first column has been transformed from whatever is being there, that is 0 0 1, and the rest 2 columns are as such. If I expand this with respect to the first column, I do get is 2x square plus x square, sorry, minus x square, that should be x square. W2, the first column is as such, the second column has been transformed to the 0 0 1. Again, if I open it up with respect to the second column, so the minus sign should be somewhere here, and if I take these two things, I would get from here 2 and from here minus 1 plus 1, so that is minus 3. Similarly, W3, the third column we have changed to the 0 0 1. With respect to this, if I am expanding this one, I would get 1 by x plus 1 by x, that is 2 by x. So, we have got Wx as 6 by x, W1 as x square, W2 as minus 3 and W3 as 2 by x. Now, we are ready to find out those functions u1, u2, u3. For that, as I said, the method of variation of parameter requires that my non-homogeneous equation must be in the standard form. Only then I can take that Rx to be the special one. So, in the standard form, if I write, that is, I will divide my equation by x cube to make this part, that is the coefficient of highest order, to be 1. If I am dividing it by 1 by x cube, I would get y triple dash plus 1 by x y dash plus minus 2 by x square y dash plus 2 by x cube is equal to 1 upon x to the power 5. That is, now my Rx is this x to the power minus 5, it should not be x to the power minus 2. Since the method of variation of parameter where we are taking is this Wi upon Wx into Rx, that Rx must be from the standard form. It should not contain any coefficient of the highest order derivative. That is why we have to make it sure that is this we are getting is x to the power minus 5. So, Rx is 1 upon x to the power 5 and W just now we had find out as this one. So, W and W1 are this one. So, what will be U1? W1x upon Wx times Rx. Now, substitute this x square upon 6 by x into 1 by x to the power 5 dx. This would give me 1 by x times x to the power 3 divided by x to the power 5 dx, that is x power minus 2 dx, its integral. I would get it as, again I have explained it here, all the process of the integration. Finally, we will get minus 1 by 6x. Now, what will be U2? Wx is 6 by x, W2 if you remember we have got minus 3. So, and Rx is 1 by x to the power 5. So, W2 by this formula we would get minus 3 divided by 6 by x into 1 by x to the power 5 dx, which will simplify to me as 1 by 2 minus 1 by x to the power 4 dx. Integral of this would be 1 by 6x cube. Then U3 square W3, that is 2 by x, Wx is 6 by x. By the formula we will get W3x upon Wx into Rx. So, substitute these values 2 by x upon 6 by x into 1 by x to the power 5 dx. I am getting it as 1 by 3 times x to the power 5 dx. Its integral gives me minus 1 by 12 x to the power 4. So, what we have got u1x as minus 1 by 6x, u2x as 1 by 6x cube, u3 as minus 1 by 12 x to the power 4. My y1 was 1 by x, y2 was x and y3 was x square. So, what should be my yp? u1x y1x plus u2x y2x and plus u3x yx. So, let us substitute minus 1 by 6x into 1 by x plus 1 by 6 cube into x minus 1 by 12 times x to the power 4 into x square. Simplified, minus 1 by 6 x plus 1 minus 1 by 6 x square plus 1 by 6 x square, and from here again minus 1 by 12 x square. What's up? Finally, it gives minus 1 by 12 x square. So, this is what is my yp. So, what will be the general solution? YH would be C1 by x plus C2x plus C3x square, and yp is minus 1 by 12 x square. We are getting this as the general solution of the given non-homogeneous differential equation. That was the third order non-homogeneous Euler-Cauchy equation. We were getting it. This solution B2C is, that is all my solutions 1 by x, x square and 1 by 12 x square, all are the linearly independent. Let us again see how the graph this look like. So, for graph we have to give some values for C1, C2, C3. First I will choose yp as this one. This is a particular solution of that given equation. The general solution is this one. So, here if I choose C1 as 12, C2 as 3 and C3 as 1. Remember here this is not going to give me this equation is not solvable at 0. We have to take the interval after the 0 of the solution. This function is not continuous at actually at 0. So, y1x would be this, I am denoting the first solution, that is where I am putting these particular values for C1, C2, C3 as this one. Similarly, let us take another one, that is C1 I have taken as minus 12, C2 as 2 and C3 as 0.5. Then another solution I am writing it. So, now I am just showing you the graph of this yp, that is one particular solution in which the solution of homogeneous equation has been taken as 0 only, and here the solution of homogeneous equations we have taken some particular values, just like that I have chosen, it is not with any initial values. So, we do get this solution. Here you see is that minus 1 by 12 x square, this is this what we are getting is that line which is completely coming on the x axis showing, but it is little bit slightly down to this one and then it will go up. And here this is the solution y2 where I have taken C1 as minus 12 and here this is with C1 as plus 12. So, that is on these sides we have taken these two solutions. So, what today we had learned? Today we had learned the non-homogeneous differential equations, linear one for the nth order in general one, that is. So, we had learned the second order linear differential equations, homogeneous, non-homogeneous, then we had proceeded further for the higher order one, and we have done in general the nth order linear differential equations, homogeneous as well as non-homogeneous. We had covered the coefficients to be the constant and the coefficients to be of the form or the general form that function of x, but they has to be continuous for the solution to exist. So, we could solve all those equations. We had seen in between also that where are the applications in the engineering modeling. I have taken very simple applications just to show that is how we can model those simple systems by the terms of differential equation and we can get the solutions. We can check it with this one. So, that is what we have done with this linear differential equations. That is all for today. Thank you.